Good afternoon. Today, we're going to do columns, and it's going to be regarding buckling. Okay, the topic today is buckling. So if we go back to the textbook, did you all use textbook when Dr. Koshi was teaching 2P? Yes or no? Okay, no, okay. So Dr. Koshi covered concept of stress and strain under axial loading. Okay. He did torsion, not everything of it. Pure bending, again, he did not finish. I mean, it's an introduction. Okay. Then you have analysis design of beams for bending. That's where you come and look at your shear force and bending moment diagram. Then you have shearing stress in beams and thin wall members. You guys were not taught thin wall members because of time. Transformation of stress and strain. You have not done it before yet, which will be covered in this course. Principal stresses under given loading were covered by this course. Deflection of beams, you have not done it. I'm going to start from chapter 10. The worst. Not the worst, okay? I think it's something that you guys will grasp easily and something new, such that you won't fall asleep. Okay, so we are going to do columns. Okay. Just a very quick, brief introduction of columns. You have to remember your second order differential equation. Are we clear? It's like when we started with 2Q, you have mechanical vibration. Again, second order, this is about the same. Okay, so we are going to start from chapter 10. So critical load will occur, or critical load before buckling will occur. Okay. The formula is such that the critical load is PCR, which is critical load. I will define them later, which is equal to pi squared EI over L. Okay, L squared, I beg your pardon. So your critical load, PCR, this is your critical load. It is in Newton, or it can be in pound force. And then we have E, which is our Young's modulus. Again, this is in Pascal or pounds per square inch. And we have our I, which is equal to second moment of area. Again, it can be meter squared or it can be in inches, meter squared. No, 4, sorry. And then we have the length, which is length of the structure. So this is in meters and this is in inches, okay? And with equation number 1, if we were to calculate stress CR, okay, which is a critical stress, all we need to do is PCR divided by A. Okay. So in this aspect, this will be equal to pi squared EI L squared divided by A. Okay. And on a side note, that we have R squared is equal to I over A. Okay. Before I go any further, let me define what the terms. This is our critical stress. This is in Pascal, okay, or PSI. And we have our A, which is our cross-sectional area. Again, this is in meters squared or inches squared. On the right-hand side, we have R, which is correspond to the radius of gyration. Now, this R value is you can find from a lot of handbook. Okay, so just briefly, so the units should be in meters. Okay, so if you look in your hand or on your textbook, you downloaded the textbook already. We know nothing. Yes. Okay. So if you go right down below on the last few pages, right, where you have structures. Okay, so let's look at a typical I-beam. So if I were to zoom in, can you see Rx and Ry? Yes or no? That is the radius of gyration, and the radius of gyration is computed by using second moment of area, I divided by what? A. Right. So from here on, by looking at what is going on into equation number 2, we're going to substitute R squared into equation number 2. So equation number 2 have the aspect of looking at critical stress is equal to pi squared E over L squared over R squared. Okay. And then finally, this term is equal to pi squared E over L over R squared. Now, the term L over R is known as the slenderness ratio. Okay. The L over R term is known as the slenderness ratio. And always remember that buckling okay, only occurs when structures are under compression, axial loading only. Can the last person in the classroom see my handwriting? Is this okay? Is the ink too thick, too thin, or this is fine? Are we good? Thank you. If you have any question, please tell me, because this is annoying. It's like I'm not here. You get what I mean? Okay, so just say, excuse me, I will pop my head up. Are we clear? All right. So if we look at buckling, there are two types of buckling. Okay, so there are okay, so one is known as centric loading, and the other one is known as eccentric loading. Okay, so what is the difference? Or yeah, what is or are the difference? So if I have a beam, okay, and coming through is a green line, okay, and the green line, what we call this is known as our centroid, okay, and the load is applying E, okay, so the load is applying along the what? Centroid axis. So we'll write P is acting along the centroid. So this is what we call centric loading. Eccentric loading again, this is our beam, and the green is our centroid. So what is happening now for this case, you observe P is applied in an offset distance from the centroid. So we have an offset distance known as B. Okay. And take note, for this case, P is acting parallel to the centroid, okay, with an offset distance B. Okay, so this is what we call eccentric what? Okay, eccentric loading. Okay, and always remember they only occur in compression. Okay. Now, the mode of deformation is very different. The mode of deformation, how Barclay before, is very different from a load that under axial loading that has very big radius or very wide thickness. Let me elaborate, okay? So let's look at compression, axial loading. So on the left-hand side is a non-slender rod. On the right-hand side, we have a slender rod. And I'll show you what is the difference between slender rod and non-slender rod. So on your left, this is the non-slender rod. Okay. So assuming that we have and then I'm going to sketch. Okay, so this is a bit of 2P stuff. And then I'm going to have the load coming here at P. Okay. So upon when the or initially there's no P yet. I do apologize. Okay, let's get rid of the P. And then when we apply P on the next image, okay, on the next diagram, when we apply P, right, what will happen is we have a when we apply P, right? We have a deflection. So the deflection, as you can see over here, this is known as your delta Y. Okay. So if I'm going to start introducing transformation, X, Y, rotation about Z, what we have is the deflection in the Y direction is equal to PL over AE. And for this case, over here, this distance is your, I will call this L. Okay. And over here, A is your cross-sectional area. Does this look familiar? Yes or no? This is really, really familiar to all of you now. Okay. Now, if it is a slender rod, okay, if it is a slender rod, it's different. So when it is a slender rod, what will happen? Eugene is definitely not a slender rod, okay? Right? Okay. So what we have over here is a slender rod. You see the difference now, yes or no? One has a wider width. Slender rod is a narrow width. Upon putting the load, so now we introduce a load. What will happen now